the same. All right, we are now recording. Let me... Well, I have a black screen. What is going on here? There we go. It's just a bit slow. All right. Okay, I think we're where we need to be. All right. Friday and over the weekend, I did finally get around to updating your syllabus, and I put it on Blackboard under content. Okay. I also I'd already done the research paper changes, and I put that on Blackboard under content. And I did my locator card and put that on Blackboard under content. Then I put all of the PowerPoints for this class out there, okay? They're by chapters, so they're really long. And even sections we aren't covering, I can't take those out. So the whole chapter PowerPoints are there. You'll just have to go through and see the ones that are important for you. Okay. Then I tried to upload the recordings that I did last week to Blackboard. They were too big. Blackboard couldn't take them all. So I talked with the folks, and they said, well, the best thing to do is load them into YouTube and then just do a link to YouTube so they don't get loaded into Blackboard. They just get linked to Blackboard. So I started doing that. And the very first one I started, after about 2 hours, it finally came back and said it was too big for YouTube. So I called someone and said, look, I was told this was going, oh, well, YouTube will limit you to 15 minutes. Well, why did we do the Screencast-O-Matic that gives you unlimited if YouTube can only do 15 minutes? Oh, but you can get YouTube to extend that for you. You have to do this, that, and that with your cell phone. I said, I don't have a cell phone. Believe it or not, I'm the last person in Alabama without a cell phone. Okay. So, and they said you had to have a cell phone. So I thought, well, I have to wait till this weekend when I'm at home with my wife. She has a cell phone. We can do it then. Well, when I got on the thing to do it, I found out you didn't have to have a cell phone. They told me you did, but you didn't. But anyway, I got that, so it was uploading to YouTube. But I still got to manage to get the YouTube link to Blackboard. And I haven't got that figured out yet. I think it's probably pretty simple, but I just haven't had a chance to do it. Last night, I was uploading the recordings to YouTube on this computer in the den, and in the office I was doing my other classes, getting those syllabi ready and things. So I was working on two computers, going back and forth, and it was somewhat of a pain in the neck, but it was doable. Theo, right? All right, the faithful three are here. We, like I was telling earlier, Treddy Lewis Gray, who was on the roll, is no longer on the roll. I guess he withdrew, but Muhammad Jovu, who we haven't seen from the beginning, we still haven't seen. He said he was going to take the course, but we haven't seen him yet. All right, so anyway, as soon as I can figure out how to get the link done, then I'll do that. And then every time when it uploads on the YouTube, which takes sometimes a while, then once it gets uploaded, then I still have to link it. So back when we were using Tegrity, sometimes 15 minutes it would be done. Now it's going to be probably sometime this afternoon, mid to late afternoon probably, before it gets done. Okay, but I'll get it done as soon as I can. I'll try to figure it out. If my work study, the guy who's going to be my work study student comes by, he's really good at this, and I think he can speed it along a lot faster. but we'll see. All right, but anyway, that's where we are now. Okay. Okay. Now, this is, nope. Sometimes when you zoom in like this, everything does handsomely. Supposed to just expand that, but now it's cutting off that last bit. Not bad, but there's no way, and it just sort of does it randomly. When I was using Integrity, all I had to do was go to get my pen activated, and then it would fit the screen perfectly, okay? I can't do that now because if I go to activate my pen, it reduces it again. So we're just going to have to live with it like this. This is as good as Integrity. It just doesn't seem that way. Okay. It's cheap. Yeah. Okay. Okay. Now, I know only one of the three. Oh, do you have a book now? All right, good. So we got 2 out of 3. So I'll still probably read too much of this just so you can follow along. So far, we have focused on the area of area interpretations using integration. Okay, that's one thing integration does for us. And here is a problem. Okay, water flows into an empty bucket at the rate of R of T liters per minute. That's the rate, R of T. R of T. Okay? How much water is in the bucket after 4 seconds? Okay? So when they say an empty bucket, when time t is equal to 0, of course there's 0 water in the bucket. But then it flows in at a rate of R of T, which looks like it starts really slowly. You're just turning on the knob and you're turning it really slowly. Now these are seconds. So very little water comes in the first second, but you're still turning it up, and now it's coming in faster and faster, and between 2 and 3 seconds you reach all the way open, but you see the water's going to overflow, so you start closing it. I'm just making this up. And you start closing the valve until you get down here and it doesn't come in anymore, but you fill the bucket. Okay? So that's why R of T is a variable function. The rate varies because you're twisting the knob. I'm just making this up, but you know, that fits, doesn't it? So the quantity of water in the bucket is equal to the area under the graph of R of T, of the function R of T. Okay? The flow rate, R of T. Now, how much water is in the bucket after 4 seconds? Okay? And if the rate of water flow were constant, say 1.5 liters per second, then all we'd have to do was say 1.5 liters per second times 4 seconds. That would be 6 liters, right? Just multiply, okay? But this isn't constant. This is a variable rate, okay? Suppose, however, that the flow rate varies as in this figure. Then the quantity of water is equal to the area under the graph of R, y is equal to R of T. To prove that, let S of T be the amount of water in the bucket at time T. So S of T, why they chose S, I would have said A of T, but S of T, that's fine, would be the amount of water in the bucket at time T. Okay. Now, if that was true, oops, wrong pen. Okay, so if, oh yeah, that's right. I can't write on the slide and keep it expanded, so as soon as I do this, it's going to shrink, but you'll just have to live with a smaller thing, and then I also have to change my color to black. Okay. So, if S of T is the amount of water in the bucket at any time T, okay, then the time rate of change of that, S prime of T, that is actually your R of T, right? That's the rate at which it's filling the bucket, okay? So that's their next statement here. Okay? Because S prime of t is the rate at which the quantity of water is changing, and we also know that S of 0, the amount of water in the bucket at time t equals 0, is 0. So now we have what they call an initial value problem. Okay? And by the fundamental theorem of calculus part 1, then we could say the S of t is the amount of water in the bucket at any time is, well, the integral of S prime of t dt, okay? But if we put the limits on here from 0 to 4 seconds, now you've lost the t dependence, and now this is just S of 4. This is so awkward to have to do this way. So that is what S of 4 is. Well, and the reason for that is S of 0 is equal to 0. So if S of t was the integral of S prime of t, which it is, and then you put the limits from 0 to 4, since S of 0 is equal to 0, S of 4 then would be that. The antiderivative of a derivative is the function, S of t, and that would be S of, going around the circles there, that's your S of 4. If that initial value was 0, okay? More generally, the S of t2, used to be so easy to make mistakes. Still easy, but it's harder to clean them, okay? Okay. S of t2 minus S of t1. In other words, say if this were t2 and this was t1, t2, then the difference of those is then the area in between those two times. Okay? That's the net change in t over an interval from t1 to t2. Okay? So then the fundamental theorem of calculus, part 1, then says, theorem 1, the net change, oh, I bet you I can do this just by doing, yes, here it is. And that's what I just wrote down, but you're not going to see the whole thing on here because it's going, I'm pretty sure, cut off. It does a little bit, but not bad. The net change as the integral of a rate. Okay? The net change of S of t on the interval from t1 to t2 is given by the integral from t1 to t2 of S prime, which is your R of t, dt, and that would be S of t2 minus S of t1. And that change over the time, t1 to t2. Okay? Now, it seems like to me they're using an awful lot of words and going into great detail to explain something that seems like it's pretty simple. So don't let the words get in your way. If you understand it, it's fine, okay? But since they're taking the effort to do it, I'm trying to do it. So let's do example 1, and I don't believe there is, oh man, I forgot to do this. Yuck. I don't know if I can do it now that I've started it. Let's see if I can. I sure don't want to end this show. I want to minimize this. Does anyone know how to minimize? Well, let's see. Let me see if I can stop. Okay. All right. Let's see if this will work. I think it should, but I don't know for sure. Here's example 1. Water leaks from a tank at the rate of 2 plus 5t. So here we have our tank. And it has a little hole in it down here. and the water is leaking out at a rate of R of T is equal to, I'll put R sub L, that's the leakage rate of T is equal to 2 plus 5T. A variable rate, by the way. That's liters per hour. That's your units. Where T is the number of hours. T is in hours. Since 7 a.m. Okay, so it started leaking at 7 a.m. Okay, how much water is lost between 9 and 11 a.m.? Okay, I thought it was going to be a more involved problem than this, but it really isn't. This R of T, rate of loss, this, by the way, is S prime of T, right? As we did before, is equal to 2 plus 5T. Okay? Now, if 7 a.m. was our initial time, what would 9 a.m. represent? T equal to how many hours since 7? 2. And 11, this would be T, let's call that T1. T2 would be 4. Okay? So here we have our situation. What would be the integral that tells you how much water was lost? S of T would be the integral of S prime of T dt. Sorry about that thing collapsed. Okay. And if you're doing this from T equal 2 to T equal 4, where your S prime was 2 plus 5T dt, what is that antiderivative? 2T plus 5T squared over 2. Evaluate that from 2 to 4, and what do you get? Help me. Say again. Okay, you may have answered. I can't hear well, though. You plug in 2 times 4 is 8 plus 5 times 16 over 2, right? Minus 4 minus okay. Now, obviously, 2 will go into 16 8 times, and 2 will go into 4 twice. This will be 8 plus 40, right? Minus 4 minus 10. That would be 4 plus 30, 34 liters of water would be lost in those 2 hours. Okay? Okay, sorry about this. Okay? Now, I'm sorry, the book did it slightly differently. It's losing at a rate of this, so all my answers is it was lost. How the book did it, because it's losing water, the amount of water in the tank at the end would be less than it was at the beginning, so they call it a minus 34 liters, which is fine then, because this is a loss of water. They put the minus here in front, and then you put it in front of your integral, and it all comes out to be just a minus 34. I was just saying it was losing that amount of water. I didn't put the minus sign in there because I was saying the term you lose it. As long as you either verbally or mathematically account for the fact that it's lost, it's fine. But their answer is negative 34 liters, okay? Or the way they write it, the tank lost 34 liters between 9 and 11, which is exactly what I said. All right. Now, now I have a question for you. In your last course, did y'all do some of the in fact, I'm trying to remember if you've even had that. Said in the next example, we will compute using trapezoid approximation, which doesn't come up until section 7.8. So I was going to ask if y'all have had this. I thought, no, Cal 1 didn't do this. This is Cal 2. Why are they giving you this now? Well, we'll figure it out, okay? So let's go to, and let's see. There's a certain thing that you have to do here. And what it is erase all the ink on the slide. And for some reason, it's not doing that. And it's not allowing me to do that. So that means I have to unwhite the screen. This is so bizarre how they do this. Well, I can't get the cursor to move. Okay, and then I have to go to another white screen. All right. So here's example 2. Let's see. Let me just make sure. Oh, sorry. I'm going to use this screen. Okay. I got to thinking, I bet you they showed this table, and they did. All right, and for some reason it cuts it off. The number of cars per hour passing an observation point along a highway is called the traffic flow rate. Okay. I don't know if you have ever seen a road that has a little strip, a wire that's running across the road. That every time your wheels cross over, it's counting the number of cars, approximating the traffic flow rate. And if they're doing that per hour, then it sums those up over the hour. So this would be the data that you would get out of that, okay? Or you have a guy there with a counter, okay? Usually those things are cheaper. Okay. It's called the traffic flow rate in cars per hour. Which quantity is represented by this integral? Okay. Of course, when I go to write, it's going to shrink again. All right. Which quantity is represented by this integral? The integral from T1 to T2 of Q of T dt. Okay? And Q of T is the traffic flow rate. Okay? So this is cars per hour, Now, what quantity is represented by that thing then? Well, depends on what T1 and T2 is. You pick a T1. Any time that's up there, you pick it. T1. 7:45, is that what you said? Okay, 7:45, that's your T1. What's your T2? 9 o'clock. Okay, there's your T2, T1 to T2. Okay, so what quantity are you represented by that? Okay.
0.75 to 2.
Say that again.
0.7. Yeah. 0.75 to 2. This is per hour.
Okay. So 1.25 would be from here to there. Is that what you're saying?
Yeah.
Okay. That would be the time, but what number do you multiply by the time? Well, actually, and it depends on how you do this, what I would do would be, this is in cars per hour. Remember, that's what the Q was. So this would be from here to here. That would be, and you get to choose which you want to approximate. If you want to say 1844 to there, this is cars per hour, but it's only a quarter of an hour. So I'd say a quarter of this, plus a quarter of that, 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 and stop. If you count the first one, don't count the last one. Or you could do a quarter of this, plus a quarter of that, plus a quarter of that, plus a quarter of that, plus a quarter of that. That would be another estimate, okay? But this one would probably be an overestimate. That one would be the underestimate. So the trapezoid rate is going to average the two, okay? So it would take the average of these two, okay? A quarter of that number plus 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 a quarter of that number, okay? But if you think of what you just did there, okay, the average of this is adding these two together and divided by 2, right? So basic, and then this would be adding these two together and divided by 2, that 2. Well, so if you just stick this divided by 2, well, you got to do it by a quarter too. So that would be dividing by 4. This one you added here and added here, so just divide that by 4 and just by your 4, okay? And then so what you actually wind up doing is this number, 1844 divided by 2 to get the average, 4 because it's a quarter, so that's dividing by 8, plus 1451 divided by 4, because you're using that twice, plus 1378 divided by 4, plus 1155 divided by 4, plus 802 divided by 4, plus 542 divided by 8. Okay? And if you think about it, remember we did this one way and divided by 4. And then we did that one divided by 4, that one. And the other way we divided this one. So in both cases we divided that by 4. So basically the average between those two is divided by 4. We only did this one, so when you average that, it's divided by 2 and average this. So basically you're just averaging these two and just counting those, which is exactly what you're given. If you did that calculation, if that was your T1 and your T2, that's exactly what you're doing. That's an example of numerical integration. It's not exact, it's approximate, but it gives you a pretty good idea. Okay? Now, why they're giving you this before you even had the trapezoidal method, but what they did was left in, right in, and that's what we talked through to begin with, and then you average the two, and that gives you the same answer as you get here. Okay? So they did it 0.25 times. And by the way, they did In the book, they said 7 to 9. So you did 7:45 to 9. If you do 7 to 9 using the whole table, you would do this divided by 8, plus that divided by 4, each of those divided by 4, that divided by 8. So you just expand it a little bit, and that would give you exactly the number we're talking about. Okay. So, yes? Okay. Okay. All right. What we said we were going to do was do one way we did it. Let's do Theo chose 7:45. The book then later, the B part says, let's do it in 7 to 9. Let's do the whole thing. So basically the whole thing, if you do the left-hand end, you would be 1044 divided by 4 plus 1297 divided by 4 plus 1478. Let's just make life a little easier. And I'll do it the way the book does it too. Let's erase this. Okay. I'll just erase these two. But I think when we do it, you'll come back and see. Okay. Now, what they call the left-hand one is 0.25. Rather than divide by 4, multiply by 0.25. Times 1044 plus 1297 plus 1478. Say 1478, all right, 1748. Okay. 1478 plus 1844 plus 1451 plus 1378 plus 1155 plus 802. Huh? Did I leave off on which one? Oh, okay. Well, we're going to do it for 1, 2, 3, 4, 5, 6, 7, 8 15-minute periods, right? So you either count the first one and don't count the last one, or count the second one and don't count the first one and count the last one. Okay? You're either going to use this as your average for that 15 minutes, or you're going to use that, the left hand or the right hand. Okay. This is what they call the left hand. L sub 8 in intervals. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. R sub 8 using the right hand end, that would be 0.25 times, don't use the first one, but use the second, 1297 plus 1478 plus 1844 plus 1451 plus 1378 plus 1155 plus 802 plus 542. Now we are using the right hand, but not the left hand. So we left off this one and then 8 that way. Okay. Now, both of those give you estimates, yeah. Say that again now. Right. 15-minute intervals, yeah. What, before we were dividing by 4, now we're multiplying by 0.25. It's the same. Yeah, exactly. Okay. This is just a little easier to write this way. Okay. Now, kind of wish they had done this, but they didn't. Here's what we're doing. 7 o'clock, and 9 o'clock. Okay, we're plotting these points. Okay, the top one up here would be 2000, and this would be 0, and you know, you're plotting these points. It's at 10, 44, 12, you know, you're plotting up and then coming down, right? Yuck, why did you do that? Okay, now, this way, the first way is estimating the rectangles like this. The second way is, what color you want? A little louder? Give me a color. Green, okay. Well, I tried to. There, okay. The second way why did it not do green? Okay, now I've got green. I don't know why. The second way is using the right-hand edge. You know, and the first way is in the left-hand edge. What the trapezoid method is averaging these. So you're taking the average between those, in other words, the middle value. So what you do to get that, you add these two together and divide by 2, or multiply by 0.5, right? The sum of those two. Well, if you look at that then, you've multiplied this by 0.25 and by 0.5, that gives you 0.125, which is dividing by 8. And here you divide by 8, but then, so half of 2 is 1, so then this is just multiplied by 2.25. You see that? And this one down here only has a 0.125, but the rest of these are 0.5s. You know, these and those and those. Yeah, all those are 0.5s. I mean 0.25s, and those are 0.125s. Because these were quarters to begin with, and then you divide it by 2 again, multiplied by 0.25. So that just gets this multiplied by 0.125, which is divided by 8. And this was divided by 8, and these are all divided by 4, because you added them. So that's why they turned out that way. That's the trapezoid method. All right? And you can plug these things in, and it says the average approximately 2550 cars. You can take your calculator and do the average, but that's what it gives you. Now, why they threw that in at this point, I'm not sure. That should have been in chapter 7, you know, when we did numerical integration. But they're just doing it as a rate of change now. Okay. Beats me. All right. Now, the next topic here is the integral of velocity, which basically is very, very similar to what we were just doing. It's now that the derivative is of your displacement, which, by the way, is velocity, and your integral then would be the integral of that derivative of displacement. And this would give you the displacement during the interval from time of travel from T1 to T2. I guess I needed some more verbiage to begin with. Yeah, let me give you the verbiage. Okay. Let S of t, and by the way, I want to lose the green now, so go back to black. Okay. Now your S of t, before that was going to be amount, now it's position. Okay, that's why I would have changed the other to A of t, and that because S of t is typically used for position. position at time t of an object in linear motion, okay, straight line linear motion. Then the object's velocity is v of t, which of course, have y'all had physics yet? S prime of t, right? Velocity is the time rate of change of your position or displacement, okay? So now the integral of v of t would then be your displacement. So if you had, and this is what we're leading to here, your integral of this would be where v of t is s prime of t. So this is going to be s of t2 minus s of t1. Okay? Just like before, that was the leakage or the filling or whatever you were doing. Now it's going to be displacement. All right. Now that is displacement. Okay? Displacement can be positive or negative. However, distance is never negative. Distance traveled, if I travel this way so far and then turn around and travel back this way, the total distance I traveled is from there to there. My displacement was from there to there, much less, okay? So to do your distance as opposed to displacement, you do the magnitude, the absolute value of that velocity. Keeping that positive. Whether I'm going forward or backward, I'm still going at that rate of speed, so that you use your absolute value, okay? And in reality, that's what you have to do with this problem, and is any of these v's that are positive, you just integrate from that v to t1 to t2. But if any of those is negative, then you're integrating minus v of t, because you're always doing positive numbers. So basically, you break that integral into, every time you change direction, you break it into another segment, and then flip the sign to make sure it's always positive. It's not a particularly pleasant experience, but it's certainly doable, okay? Now, here's example 3, and I think they have a graph for it. So this won't last long, but I will blow it up for you, just so it'll be a little easier to read, especially once you get home and trying to redo this. So here is the graph of v of t. This is your velocity function. T cubed minus 10t squared plus 24t. And we're when you draw the graph of this, you notice that between t equal 4 and 6 seconds, you have a negative velocity, okay? But what you have to do with that, the speed is never negative, so the speed would be the dashed line here, okay? And that's what you're integrating, v of t. So if you want displacement, you just enter the graph of this, the integral of this, okay? If you want distance traveled, then you do 0 to 4 here, and then you do the negative of this from 4 to 6, okay? So that's theoretically what we're going to do. Let's do that. The displacement over 0 to 6. So, of course, I go to write this, and it shrinks, okay? So displacement, this would be s of t, okay? I guess we'll go on, let's call that s of t, is equal to the integral of this function, t cubed minus 10t squared, I can't write, plus 24t dt from 0 to 6. To get the displacement, that's all you do, okay? What is the integral of that function? Integral of that function. T, you're differentiating. Integrate. Yeah. T, increase the power. T4 over 4 minus 10 T cubed over 3 plus 12T squared. Very good. 24T squared over 2 would be 12T squared. Okay? Evaluate that from 0 to 6. To get your displacement, you just do that. You don't worry that it was going backward one way or another. The integration takes care of it for you. Now, I think I'm going to need a calculator to help me out with that one. 6 to the 4th power. I can do it without a calculator, but I thought maybe one of you would have it. 1292? 1296 divided by 4. I'll just write it. 1296 divided by 4 minus, okay, 6 cubed, I think, is 216. That would be 20. No, my head's not working very well today. Yuck. This is such a pain in the neck to have to do this every time. I shouldn't make errors. That's the answer, right? Okay. Okay. 216, so that'd be 2160 divided by 3 plus 12 times 6 is 72. And then when I minus a 0, get 0. I did that one. Okay. So 12 will go into, 4 will go into 1296. 3, 2, 4, right? Plus 72 would be 396 minus, now will 3 go, 3 will go into that, won't it? 3 will go into that 720. No. Is that right? It can't be.
12T squared, right?
What's that?
We have to 12T squared.
I can't hear you.
Oh, yeah, you left out the 12T squared.
Oh, that's what it was. Right. Yeah, 12T squared. Yeah, sorry about that. Okay. So that was then,
That's 430.
yeah, 12 times 6 is, yuck. This is why I shouldn't make errors. Pointer options. I can't get the eraser to do. Okay. That's 12 times 36. What is that? Wait, before you tell me, I've got to go back and do this. Such a pain in the neck. Okay. That's 12 times 36. For what?
32.
432. Okay. All right. Change this one. Such a pain in the neck. Okay. All right. All right. 324 plus 432 would be 758 minus 720. It still seems 38. Seems like it should be bigger than that. Just gut feeling. They got 36. So evidently I did something wrong there. Oh, that's it. That's a 6, not an 8. Sorry. All right. 56. I can't add. 36. So that's his displacement, okay? But what is the distance traveled? Now, they did the hard work for you here. You have to figure this out on your own before you can work a problem like that. You've got to figure out when it goes negative, okay? Now, how do you do that? There's your function. We want to determine where that's equal to 0. Well, it's obviously equal to 0 at t equals 0, right? Okay. So the other place that it's 0, well, let's do the original function, is going to be where t squared minus 10t plus 24 is equal to 0. Okay? I think we can figure that out pretty simply, can't we? T minus 6, t minus 4, right? So this is at t equals 6 and t equals 4, which is exactly what we got here. And we know it's positive in the first interval, and it's negative in the second interval. So then that gives us it. So you see, they did work for us and showed us this. If you were doing this without the graph there, this is what you would need to do to figure out where that goes negative and where it's positive, where it's negative. So to get the distance traveled, that would then be S. Let's see, what do they use for distance? I'm going to use d of t. Because I like S for displacement. So I'm going to call this d of t. Okay. D of t, oh boy, that might not be good because it looks like dt. But anyway, distance is a function of time would then be the integral from 0 to 4 of this thing, t cubed minus 10t squared plus 24t dt, minus, because you're adding a negative, so that would be integral from 4 to 6 of t cubed minus 10t squared plus 24t dt. Okay? Now our integration is the same. t4 over 4 minus 10t cubed over 3 plus 12t squared. Okay. Such a pain to have to do this every time. Okay. 12t squared. And do this from 0 to 4. And then subtract, which is minus a minus, which is in a sense adding. Same thing. T fourth over 4 minus 10t cubed over 3 plus 20. I did it again. Old dogs, new tricks, okay. No pen, that's what I want. Okay. 12t squared. And this will be from 4 to 6. Okay? Now, I'm going to need some more room, so what I'm going to do is erase some of the stuff we've already done, like the up here part. I'm sure this looks funny at home, to be erasing. All right, so evaluating these up here, this will be 4 to the 4th. 4 cubed is 64, and another 4 times that is 256. Is that right? I think it is. 4 to the 4th, 256. Huh? Is that right? 256 over 4 minus 10 times 64 over 3 plus 12 times 16. And the zeros don't mean much of anything here. And then we're going to do a minus and we already did the, why did I erase it now? 6 to the 4th, what was that? $12.96 over 4 minus, and this is 2, 1. Why is it disappearing? 2160 over 3 plus, and we did that before, 12 times 16. No, 12 times 36. What was that?
432.
Say again, 432? Okay. Okay. And then minus a minus, which is plus 256 over 4 minus 640 over 3 plus, and what was 12 times 16? 12 times 8 is 96. That's be 192. Okay. All right. Well, now, obviously, this and this are exactly the same, so that would be 256 over 2 minus 1280 over 3 plus 384 minus 1296 over 4 plus, oh, that's going to change that. We already did this one, didn't we? That was 720 minus 432. Okay. This comes up to 128, and that becomes a messy decimal, a fraction. That would be 4, 2, 6 2/3, I think. I believe that's right. Plus 384 minus 328, I believe that is. Y'all have to check my math. Plus 720 minus 432. Now, if you got calculators, do those up. This plus that plus this. Okay.
1296 over 4 is 324.
It's what?
1296 over is 324.
324. Okay. Thank you. All right. But anyway, when you add all those up,
1172.
what's that?
It's 1172.
You get 1172.
Yeah.
Well, you got a fraction in there, don't you?
I didn't do the fraction part. The 3 that
You just rounded that to.
no, I did the 3 that you connected with the lines.
I'm sorry.
The 3 that you.
Oh, adding those 3, then you have to subtract the other 3, yeah. Subtract those 3. What did you get the adding? Let me get that down.
1172.
1173,
2.
772, okay. And then when you subtract those, wow. Uh-oh, then I messed something up. You'll have to check my math. I probably did a dumb error somewhere in there. It actually comes out greater than the other. The other was 36 meters. This actually is 49 meters. Okay, so obviously I made an error somewhere. If you got a greater negative number than you had a positive number. And I'm sure I made a dumb error somewhere there. Okay. But anyway, because the distance, basically what you're doing is you're this part minus this part, or this part plus that part. Okay. And that's the difference there. And so anyway, you got to go a further distance than you had a displacement. It can never be less. Can be the same, but it couldn't be less. Okay. And then there's one final application here. Oh, wait. Yeah, okay. Here is the figurative representation of what we were just doing. If you actually show the particle is moving this way and then comes back this way. So the total displacement was 36. The total distance is 36 plus this. And that was another 128 over 3, which would be 40. 42 point something, so that would be the total distance. 42 and 2/3, I think it was. 41 and 2/3. No, 49 and 1/3. Okay, because the distance, the displacement is this 36. The distance is this plus this. I didn't have that back in. So is this part plus that part. Okay. So the curve there, it really isn't a curve, it's just so it can separate. And the t equals 0, you're here, t equals 4, you're here, t equals 6, you're there. So you add this to the aspect of that, and you come up with something a little bit more. Okay. That's the last slide. There's one other. How are we doing on time? Huh? 10:40? Okay, we got plenty of time. Okay, total versus marginal cost. I don't know if y'all have run into this before. Y'all in economics at all? I'm not either. My brother was, but yeah. Okay, consider the cost C of X of a manufacturer. I'll just write it on this slide because we got room. So C as a function of S, the cost of producing X number of units, okay, or commodities or whatever. Now the derivative of that is the change of cost per change of per unit produced, okay? That would be change of cost per change of per increase in the unit, okay? That is called the marginal cost. And they approximate that would be the cost of producing one more unit, okay? The marginal cost. The cost of producing X units would be this, and then what is a derivative? Change of cost per change of unit, okay? And if that change of cost producing one more unit, so that would be the cost of producing the next unit, the marginal cost, okay? The cost of increasing production from A units to B units would then be, the actual thing would be C of B minus C of A, okay? And that should be equal to the integral of C prime of x dx from A to B, okay? That is fundamental theorem of calculus 1. You know, if this is the derivative of this, these are the costs, this is the marginal cost, then that integral would be the difference of doing this. So that is the cost of producing whatever that increase in units from A to B, based on the marginal cost. Okay? Now, example 4 says the marginal cost of producing, and the marginal cost is C prime then, the marginal cost of producing X computer chips in units of 1,000 is, can I get all the, yeah, I'll try. C prime of X, okay, is equal to 300 X squared minus 400X plus 40,000. Say again?
4,000.
Oh, 4,000, yeah. I think I said, okay, I don't know what I said. Okay, and those are dollars per 1,000 chips. So the X is standing for thousands of computer chips, okay? Now, the A part says here, find the cost of increasing production from 10,000 to 15,000 chips. To go from X equal, and remember, X is in thousands, so X going from 10 to 15, because we're doing it in thousands, okay? So we want the cost of increasing production. Well, that's going to be the integral from 10, X equal 10,000 to 15,000 of your 300 X squared minus 4,000 X plus 40,000 dx. Now I'm going to ask you, do you know, can you think of anything to simplify that maybe just a little bit? Yeah, divide out 100. Pull out the 100 in front. Okay, so that would be 100 times the integral from 10 to 15 of 3x squared minus 40x plus 400 dx. That's going to give you the same thing. Just keep it as simple as you can. All right, what's that integral? I'll put the 100 down. Antiderivative of 3x squared is 3x to the third over 3. So those 3's go out. That's nice. Minus 40x squared over 2, which that makes it a 20. That's kind of nice. Plus 400x. Evaluated from 10 to 15. All right. So when you have 15 cubed, okay, I'm going to put the 100 out front. 15 cubed. Someone do that. 3275? 375. My hearing is so bad. 33. This is such a pain to have to do this. 3375. Okay, minus, and I think I can do 15 squared. That's 225, and then multiply that by 20. 4,500 plus 6,000. 6,000. It's 400 times 15. Yeah. Okay. And then we have a minus 1,000 plus 2,000, isn't it? Yeah. Minus 4,000. Okay. Tell you what, the way that's sitting there, I'm just going to do 100 times 2375 minus 2,500 plus 2,000. This is not the only way to do it, but it's just since it was sitting there, that way I was going to do it. Let's add those two together. That would be 4,375 minus 2,500. That would be 1,875 times 100 would be 1,87500. So that would be $187,500. That's the cost of increasing production from 10,000 to 15,000. Okay. Now, determine the total cost of producing the 15,000 chips, assuming that it cost $30,000 to set up manufacturing run. Okay. So C of 0 is 30,000. Find the total cost of producing 15,000 chips. Okay. Basically, we do exactly the same thing we did. I just don't have enough room. So what I'm going to do, if you don't mind, I'm going to erase the top part here. And I think I've got this all written down, so I don't need that anymore. And my calculations, I'll get rid of those two. And probably these right here as well. Okay, there was my answer to the first part. Now we're going to do the B part up top. There we go. Here's the B part. It says, determine the total cost of producing 15,000 chips, assuming it costs $30,000 to set up manufacturing, which means C of 0, meaning if you didn't produce a single chip, it's still going to be $30,000. Okay. So, what you have then is the integral from 0 to 15. Okay? Everything else is exactly the same. In fact, since it is the same, I don't need to write all this again. Okay, let's pull out the 100. Oh, no, don't do that. Okay, hit the wrong button, sorry about that. Okay, I can't. All right. It's the 100, 3x squared minus 40x plus 400 dx, and that was 100 times x cubed minus 20x squared plus 400x 0 to 15. Okay. This part is just what we had initially. I wish I hadn't erased all that. Do y'all still have it written down what that first part was with just the 15 in there? What was that with the 15 in there? $15 cubed. That was, don't you have it down? I erased it, sorry. 3375, wasn't it? Is that what you said? Minus 4,500 plus 6,000. Okay. Now, what we can't do, though, is do the minus 0, okay? But if you do just the top part there, let's see what that yields us. This would be 9375 minus 4,500, and that would be 4875 times 100 would be another 20. That would be 487,500. Okay. Now, but you also have the initial cost of setting up, and that they told you was going to be 30,000. So add another 30,000 to this, and that gives you your 517,500. So that would be the cost. Yeah, setting up the whole thing. All right, that finishes 5.6. Okay. Now, the last time I taught the class liked doing these preliminary exercises, preliminary questions in the exercises. Do y'all find that useful or not, or have we done it enough for you to tell? Want to do them? Okay, let's do those. What I'm going to do is go to a clean slide now. Let me see if I can erase all ink. Okay. All right, I did that. All right, a hot metal, how much time do we have?
10
Huh?
10 minutes.
10 more minutes, okay. A hot metal object is submerged in cold water. The rate at which the object cools in degrees per minute is a function f of t of time, function of time. Which quantity is represented by this integral? The integral from 0 to t, that's going to be your final temperature, no, time. That's strange. Usually capital T represents temperature, but here it's representing time. Okay? F of t dt. It says what quantity is represented by that integral. Okay? Where your rate at which the object cools in degrees per minute is a function f of t. So f of t is the rate of cooling in degrees per minute. Degrees per minute. Okay. So what would that f of t represent? I mean, the integral of f of t going from 0 to some capital time t. So the rate of cooling is degrees per minute. Okay. So basically, I mean, use your units. Degrees per minute times minutes. The t is in minutes. Okay. That would be the amount of degrees cooled in those t minutes. Right? The number of degrees cooled in t minutes. Okay? Now, I like to always check because they do have these answers in the back. And this is 5.6. Because I don't want to be telling you something that's wrong. Sometimes my interpretation of what they're asking is not that. The total drop in temperature of the metal object in the first t minutes after being submerged in cold water. Exactly. The number of degrees it dropped in t minutes. All right, the second one here. A plane travels 560 kilometers from Los Angeles to San Francisco. So this is the second one. Plane travels 560 kilometers from LA to San Francisco in 1 hour. Okay? If the plane's velocity at time t, okay, is in kilometers per hour, okay, what is the value of the integral from 0 to 1? Is that a 1? I can't read it. V of t dt. All right.
Distance traveled in an hour.
What's that?
It's the distance traveled in an hour.
The distance traveled in an hour, and guess what? We know what that is. 560. Okay? Because this would be distance traveled per hour times hour. That would be the total distance traveled in 1 hour, and we know that would be 560 kilometers. Does that mean he's traveling at a constant rate of speed of 560 kilometers per hour? No. When he took off, he was much slower, and right before he lands, he's much slower. But the velocity, of course, his maximum velocity would have to exceed that pretty significantly to get that to count. But this would represent the distance traveled in the hour, which is 560 kilometers. Exactly. All right? Y'all are catching on to this stuff really well. Number 3. Which of the following quantities would be naturally represented as derivatives and which is integrals? Oh, okay. This light is in my eyes and I'm hard to read. Velocity of a train. Okay, would that be naturally represented as a derivative or as an integral? Velocity is typically a derivative of displacement. Now, you might say it would be an integral of the acceleration. You would be okay there, but that's getting to a more complicated thing. That would typically be a derivative. Okay, that was the A. B was rainfall during a 6-month period. That would be an integral because you would integrate the monthly rainfall over 6 months, and that would give you the total rainfall. Exactly. Okay? C, Mileage per gallon of an automobile. Second? Derivative, yeah, miles per gallon, that's going to be a derivative. Okay? I got to do D somewhere else. I don't have room at the bottom. Increase in the U.S. population from 1990 to 2010. That's an integral, of course. You have the population rate of increase, difference between birth rate and death rate, that kind of stuff. And then, so that would be an integral. Y'all got it down. Okay, homework exercises here then. Do any of the odds, 1 through 7, do either 9 or 11. Any of the odds 13 through, this light is blinding. 25. Do number 27. And that's it. All right. Now, let me, also when I do these, sometimes I like to pick up on things they're talking about. I don't know, y'all have heard them talk about the one way of reducing greenhouse gases using a market thing is doing a carbon tax, okay? And that's modeled in number 20. That's not one you have to do, but if you want to, if that's an interest of yours, throwing my computer calculators around like crazy, huh? Okay. Or is that a phone? Yeah, calculator, okay. All right, so if you can apply calculus to something like carbon tax, if that's an interest of yours. Heat capacity, okay? If you're into physics, and thermodynamics and stuff like that, heat capacity is mentioned here. That would be a pretty good paper topic too. And you can probably find other things in here. Okay, how are we doing on time?
It's 11:05.
11:05. We got 5 minutes. Goodness gracious, you want me to cheat you out of 5 minutes of your tuition dollars? Oh, heaven forbid. No, we won't do that. All right. Let's see. All right, that was the last slide in this section. So I'm going to hit click to exit. Okay. And let's at least get introduced what we're going to do next. And that's what we started off to do. I think I asked you before, did y'all do substitution method in Cal 1? And I can't remember what y'all said. No, you didn't. I thought that was the case. Did you? You remember? You didn't? And I'm pretty sure you said not. So that's what we're going to get into next. This is usually where I start Cal 2. So we're not too far behind. Just about with what you call it, syllabus and all that stuff we had to do at the beginning. Why is this not opening? Maybe it's wanting to go too. There we go. Okay, see, it didn't. All right. And again, we don't have lots of time, but let's just at least introduce it. Integration, anti-differentiation, is generally more difficult than differentiation, okay? You can take derivatives of just about anything. Let me get this changed here too. Okay. All right. Now, there are no surefire methods, and many antiderivatives cannot be expressed in terms of elementary functions. However, there are a few important general techniques of integration. That's where this course was supposed to begin, okay? One such technique is the substitution method. which basically uses the chain rule in reverse, okay? And here's what it's based on. Let's just say we had to do an integral of, oops, let me get my color changed here. Okay, yuck. All right. Now, I don't know why I wound up with my things at the bottom, but that's good. I can see my own clock down here. Before I couldn't, now I can. I don't know why, but it's fine. It's actually better this way. What if we're trying to do the integral of 2x cosine of x squared dx? Okay? And this, by the way, is going to be indefinite integral. Okay? Now, there's no product rule or other thing that's going to make this particularly doable function. So what we tend to do is look at this and say, well, wait a minute. I know what the derivative of this is. You know, think chain rule. What's the derivative of this? 2x, and there we have it. In fact, 2x dx. So therefore, all we have to do is find the antiderivative of cosine. And what would that be? Sine. So my guess would be, right off the top, this might be sine of x squared. Okay? Now, how do I find out if that is indeed that? Take a derivative to see what you get. Now, what's the derivative of sine? Okay? That would be cosine of x squared. Chain rule then, times 2x dx. You've got it. So that's exactly what we're doing here. Now, if you think about what we did here, we did the 2x dx is the derivative of that. Okay? And then all we had to do was find the other. Now, the only thing that we're missing here, that answer was sine of x squared, but we got something else. Indefinite integral plus c. You got to have your plus c tacked on at the end. Okay? So sure enough, that is how we do that. Now, so far we haven't made a substitution. We're going to introduce substitution and make it a little bit easier. Okay, we didn't get much done there, but we did get a little bit. We will start in the next, it's not really an example, a lead-in to our first theorem. Not enough there for you to do any new homework exercises, so just what we've had so far, that will do. All right, good deal. We'll see you on Wednesday. And hopefully the other guy will show up sometime or another. Okay? Now that disappeared. Well, let me go and close.